Hi guys, we're going to talk about a simple method for solving numerical ODEs, or rather for solving ODEs numerically. It's called Euler's method. It goes back to Euler. It's the naive method, and it kind of corresponds to the naive method for estimating derivatives that we saw previously. That is, we assume that if we take the difference between yk plus 1 and yk and divide by the difference between the x values, which would be h, right, the interval between the x values, that should give us a good approximation for y prime. And we saw that that's true, but with the qualification that this is really a very good approximation for the point halfway between xk and xk plus 1. It's a good approximation for the derivative at the midpoint. However, in Euler's method, we actually take it to be an approximation for the derivative at yk itself. So this is what we do. Now remember, we're solving an ODE with an initial value given, so it's an initial value problem, right? So we've got a y0 that's been given to us to be the value of the function at x0. x0 we're assuming is the leftmost point of the interval on which we're trying to solve the ODE. And then what we do is, assuming that this is true for, assuming that this is true for yk, the derivative at yk is this, then we get this formula for the iteration. To go from yk to yk plus 1, you take the value at yk, and you multiply by what the formula f gives you for the derivative, right? You evaluate it at xk, yk, the two current values, multiply by h, and that gives you an estimate for what the next y should be. Now, as I say, this is a little bit naive because we don't expect that the actual average rate of change from xk to xk plus 1 would be exactly this value. This value is the derivative at xk, or at the point xk, yk, but there's no reason to think it would be represent the average value of the derivative between xk and xk plus 1. So this is a naive approach. However, despite that, it works. So let's see. Oh, here's the program, right? This is going to be a short lecture. I'm going to go right into MATLAB on this one. So I have to upload this. I don't think I've done that yet. I will upload the EulerForward function to Canvas. The 4, by the way, stands for forward. So this is, this is the forward version of the Euler method, and we will see later there is also a backwards version, and I'll explain about that in maybe in the next lecture. And the inputs are the initial, the leftmost x value, right, x0, the initial x value, the initial y value, the last x value, x end, right, the right endpoint of the interval we're working on. H is the interval that we're using to, the length of the intervals in which we're dividing up the x-axis, right, to do our approximations. So the distance between successive x values in our numerical approximation. And FCN, that's a function handle. Actually, you can also give it, I think you can give it a string that contains an expression, and or it contains the name of a function, and it will evaluate that, because down here it uses the f-eval functions to evaluate functions. So I think it'll evaluate other things besides just function handles. But actually, I think this is kind of an older way of doing things before function handles became available. So I'm just going to be giving it a function handle. Okay, let's see. It returns, by the way, it returns a list of x and y values. So it returns all the xk values, x0, x1, all the way up to, whatever the last x value is at x end here. And it also gives you the corresponding list of y values and all those x values. The whole code is really here. It's really just 7 lines, right? That's all it takes to solve an ODE numerically, right? Much harder to solve ODEs symbolically using mathematics, but to solve them numerically, it's actually pretty easy in a sense. Let me just mention one thing. This function fix, that is like kind of like a floor function or a ceiling function, except fix works by always rounding the input towards 0, right? So for example, fix of 1.9 is 1, but fix of negative 1.9 would be negative 1. If I applied the floor function to negative 1.9, it would be negative 2. If I applied the ceiling function to positive 1.9, the value would be 2. So fix is a kind of a cross between the floor and ceiling functions. Right? So it rounds the number towards 0, to the nearest whole number closer to 0. And we just do this to get a whole number for n, right? So the number of subdivisions of the interval should be the length of the interval, which is xn minus x0, divided by h. That may not be exactly a whole number, so we just round it off to the nearest whole number, and actually then we round up. So I think this is really kind of equivalent to the ceiling function. One other thing here, let's see. We use the linspace function to divide the interval up, or to get a list of the points in the interval after it's been divided up. And notice that we apply a prime to it. That's the transpose function. So linspace returns a list or a row vector, and then they apply the transpose function to it so that x is actually a column vector then. So x and y are both going to be column vectors, y also, and we initialize y just to be all zeros, and then we can immediately set the first y value to be the y0 that we were given. And then for all future y values, we go through a loop where we apply the formula that we saw earlier, right? So we apply the formula, oops, I did it again. We apply the formula here that the new y value is equal to the old value plus f times the value of the function, our f function that represents the derivative evaluated at the previous point, xi minus 1 and yi minus 1. Very, very simple, right? Just 7 lines of code and it will solve differential equations. Okay, let me switch to MATLAB. So I think what I'll do is I'll start by redrawing that vector field that we had the other day, so we can kind of see intuitively how the solution matches up with the vector field. So I think what we did, we had a mesh grid or a rectangle where the x values went from 0 in increments of 0.5 to 5, and the y values went from 0 in increments of 0.5 to 4, right? So doing that, okay, so those are our x and y values. And, right. And let me do the, oh right, and then I want to say that, let's see, Ex is going to be a matrix of all ones. That's the x component of all the vectors, so that was, I think it was, in this case it was 9 by 11, right? 9 by 11. And then the dy, oh, I have to enter the function. I think I did that. Yeah, here it is. So there's the function. This is the function f that calculates the value of y prime at any point x and y. And so we can just use that to get dy. dy equals f of xy right, okay. And now we can try the vector field. So quiver x, y, and then dx, dy. There we go. Let me see if I can make this stay fixed. Okay, yeah, so there's the vector field. Now what I'll do is I'll try to plot the solution over it, right? And you can see how they line up. Oh, by the way, one thing worth pointing out that I didn't mention the other day when I had the vector field handy is that, let me see if I can make this bigger. You can see by looking at the vector field where the the ODE is well-conditioned. Remember that the definition of well-conditioned was that the derivative of f, the partial derivative of f with respect to y, is either, well, not either negative or 0, right? Less than or equal to 0. So you can see that in the arrows. If you look at a column of arrows and compare how they're changing as you go up the column, that is going to tell you how, that's going to tell you how f is changing as you change y, and then you can tell whether this derivative with respect to y is positive or negative, right? So for example, in this column here, as I go up, we see that the arrows get more and more negative. The slope becomes more and more negative. So in this, along this column, well, let me qualify that. From this point on, the arrows are getting more negative. From this point down, from this point up, the arrows are actually getting more positive. So what we can say is that in this region here, it seems that the ODE is not well-conditioned, but in this region here, the ODE is well-conditioned, right? So it can change its conditioning depending on where you're looking in the domain. Another example, how about the very beginning here, right? You can see that in this column here, as you go up, the slopes get bigger, so that says that Fy is positive here. So it's not well conditioned on this region. However, once you get to about here, it seems that now y prime starts to decrease, so Fy would be negative over here, and therefore it would be well conditioned in this region, and probably in this region generally. Okay. Now, another notion we talked about the other day was stability, and I can say more about that when I plot the solutions. So let me use the Euler function to work out the solutions. Let's see. So let's say that xs and ys. Let's say the solutions, s for solution, let's say in this case. So the solution is going to be Euler, oops, misspelled Euler, Euler 4. We want to start, why don't we start at x equals 0, and why don't we throw in an initial value for y, I don't know, maybe 0.5, I don't know. So it'll start out here, right? That'll be where the function starts out. And now looking at the vector field, you can kind of see the course it's going to have to take. It's going to have to go something like that, maybe go down, something like that, right? Then the next entry was, the n value for x. So we want to go up to x equals 5, really, right? Why don't I go up to 6? Okay. And then we want the h value. Why don't I start with a relatively large h value of 0.1? And then finally, we have to give it the function f that determines the derivative y prime. Okay, and let me suppress the output. This is going to be rather large. Oh, that was easy. It didn't take very long to calculate that. Let's plot the solution. Oh, what I should do is before I plot it, let me set the hold on, so we'll keep the old graph while we plot the new curve. Now I can plot x's, y's. Ah, there we go, yeah. So here you can see the solution, or the approximate solution, right? So it does line up fairly well with the vector field, right, as it should. Now, one of the things you can play with here is you can see what happens as you make the h value smaller. So let's try reducing the h value. Let's cut it in half, right? So let's make the h value 0.05 instead of 0.1. And now I'll plot that. They're pretty close together. It didn't make too much difference, but let me try zooming in here. Let me see, where do they seem to be particularly? Yeah, here we go. Okay, let's zoom in. All right, so I believe the first one was when h was 0.1. The second one is when, or the yellow one is when h is 0.05. So presumably the second one is more accurate because it has a smaller h, right? So it seems that the true value is probably over in this direction somewhere, right? But let's see what happens if we continue reducing h by a factor of 2. So let's go to 0.025. Yes, now you can see that here's h is 0.1, 0.05, 0.025, and you can see that, yeah, it does seem that the true answer, if we were to continue this to the limit as h approaches 0, it seems like the true answer would be down here somewhere, right? Let me do this one more time. So I'll change it down to 0.0125. Yeah, and you can see it's still continuing. Now, notice the distance between these successive curves. It seems like this distance is about twice the next distance, and that distance is about twice the third distance. So it seems that, roughly speaking, it seems that the distance between these is dropping by 1/2 every time we change h by a factor of 1/2. In other words, it seems that the change in these in the plot is proportional to h. And when you know that the change in the approximations is proportional to h, that also suggests that the error is proportional to h. So, and we will see this later. We will show this more precisely later. But that is, in fact, the case with the Euler algorithm, that the error in the approximations is proportional to h. And we'll be able to use a form of Richardson's extrapolation to get an even more precise estimate and a good estimate of the error that way. Okay, now let me zoom back out. Let's try. So after zooming back out, what I've done is I've plotted two other curves with a low h value, but two other curves that simply differ in their starting points. So this lower blue curve starts at 0, so the initial y value is 0, and the other curve starts at 2. The initial y value is 2. And you'll see that in both of these cases, although the curves start out at different places, they approach the middle curve, right? They get closer together over time. So that would suggest that this ODE is strongly stable. Remember that stability was the property that if you make a slight change in the starting point, right, the starting value for y, that you only get slight changes in the further evolution of the curve, right, as you solve the equation down the line. And specifically it said that for small changes in the initial value, the changes later are always linear in that initial change. And in this particular case, that seems to be strongly true, that even if we start off with epsilons, right, changes in y that are not even particularly small, that the curves just get closer and closer together, so that the changes in the function eventually kind of approach 0. Or at least on this interval, right, this interval from 0 to 6, that seems to be the case. Right? It may not be true in other intervals. It may not be true at other starting points. It may be that you can start somewhere else where the solution will not be stable. But it does seem to be stable here. Okay, see you next time.